In this lecture, we'll discuss the vapor compression refrigeration cycle. Earlier, we have discussed a heat engine operating on a Carnot cycle with the working substance in liquid and vapor phases. We saw that the primary challenge in realizing the Carnot cycle is compression of wet vapor. The modification of this process results in the Rankine cycle that we have studied. We now turn our attention to a refrigerator or a heat pump. A refrigerator or a heat pump is a heat engine operating in reverse. So, a refrigerator works between two thermal reservoirs at low temperature and high temperature. But unlike a heat engine, the refrigerator consumes work and it absorbs heat from a low temperature reservoir and rejects heat to a high temperature reservoir. Therefore, a Carnot cycle in reverse corresponds to a refrigerator. A refrigerator operating on a Carnot cycle will have the highest COP, and the COP is independent of the working substance. This is just similar to a heat engine operating on a Carnot cycle, which has the highest efficiency, and efficiency of a heat engine operating on a Carnot cycle is independent of the working substance. Irrespective of the working substance, a refrigerator working on a Carnot cycle in reverse can be depicted on a TS diagram with these four processes. So heat is absorbed in this process going from state 1 to state 2, and this heat absorption takes place at low temperature TL. And in a typical refrigerator, this process takes place in the evaporator section. Then the working substance is compressed to a higher pressure corresponding to higher temperature TH in a reversible adiabatic manner, that is in isentropic fashion, and this can be done using a compressor. And then the heat is rejected during the process 3 to 4 at a high temperature TH, and heat is absorbed at low temperature during process 1 to 2. So this heat rejection from 3 to 4 also takes place at a constant temperature, and typically this would take place in the condenser section, and thereafter the working substance is brought back from state 4 to state 1 through isentropic expansion, and theoretically this can be done using a turbine to expand the substance from high pressure to a lower pressure and correspondingly higher temperature to a lower temperature in an isentropic manner. A refrigerator that operates in a Carnot cycle differs from a heat engine in a way that the cycle now just runs in the reverse. Note that in general the capacities of refrigeration and heat pump devices are generally much smaller than a power plant, and power plants can give output up to 1000 megawatt, but the capacities of refrigeration and heat pumps is significantly smaller. Similar to a Carnot heat engine operating with a pure substance in liquid and vapor phases, we can have a Carnot refrigeration cycle with vapor in the system. Therefore, the simplest way to have this Carnot cycle for a pure substance that can be in two phases, liquid and vapor phases, is to have this Carnot cycle within the liquid vapor saturation dome. And there are many other ways of having this Carnot cycle on this TS diagram, but this is the simplest way as we have seen for a heat engine. So when this Carnot cycle is executed in this manner, that is within this saturation dome, then process 1 to 2 corresponds to vaporization of the working fluid, and therefore this takes place at constant temperature as well as constant pressure that corresponds to the saturation pressure corresponding to temperature TL. Similarly, heat rejection, that is from state 3 to state 4, takes place during the condensation of the saturated vapor at state 3 to a saturated liquid, and this takes place at higher pressure because the line 3 to 4 is an isobar and also an isotherm within the liquid vapor region, and the pressure for process 3 to 4 remains the same, and that is equal to the saturation pressure corresponding to the high temperature TH. Among all these processes, isentropic expansion of the saturated liquid at state 4 to wet vapor at state 1 is difficult to realize in practice. Moreover, the substance during process 4 to 1 will be mostly liquid. Therefore, if a turbine is used to isentropically expand the substance from state 4 to state 1, there will be little work output from the turbine. Therefore, it is not worth the cost of including an equipment such as a turbine to execute process 4 to 1. Therefore, in practice, the turbine that is required for executing the process 4 to 1 is replaced with a throttling device such as a valve or a capillary. And in this throttling device, the working substance is throttled from high pressure, that is at state 4, to a low pressure at a new state, let's say state 1 prime. And this throttling process is irreversible process and is accompanied by an increase in entropy. The idea of having this throttling process is to reduce the pressure of the working substance from pressure at state 4 to pressure at state 1 prime, that is equal to pressure at state 2. So this cycle that is shown in this blue color, that results from the modification to the Carnot cycle, that is cycle 1 prime to 2 to 3 to 4 and back to 1 prime, is called the vapor compression refrigeration cycle. So this vapor compression refrigeration cycle can be executed in this simple vapor compression refrigeration system. So the process 1 to 2, that is absorption of heat from the refrigerated space, takes place in the evaporator section, where the inlet is state 1 and the substance exits the evaporator at state 2. The heat that is absorbed by the working substance per unit mass is QL, and the working substance exiting the evaporator is at state 2, which is fed into a compressor that consumes work WC, and it raises the pressure of the working substance to pressure at state 3, that is the saturation pressure corresponding to the high temperature. Thereafter, this hot working substance, which is at state 3, is at a saturated vapor state, is passed through a condenser section, which is essentially a heat exchanger that rejects heat, and if the system is used as a refrigerator, then the condenser rejects heat to the ambient conditions and the evaporator absorbs heat from the refrigerated space at a lower temperature. So the working substance exits the condenser at state 4, where it is a saturated liquid, and thereafter the working substance is brought back to low pressure at state 1 by this throttling device, which is essentially a valve or a narrow capillary which reduces the pressure of the substance flowing through it. In practice, another modification is made to this vapor compression refrigeration cycle so that this isentropic compression step from state 2 to state 3 has only pure vapor, that is superheated vapor. That is, it is practically more convenient to have a compressor that handles only vapor than a mixture of liquid and vapor. Therefore, this process 2 to 3 is modified in a way that the vaporization step that takes place in the evaporator, that is from state 1 to state 2, is continued till this point 2 prime, where the substance is a saturated vapor. Thereafter, compression takes place in a reversible adiabatic manner so that the entropy remains constant. So heat is rejected in the process going from state 3 prime to state 4. Therefore, in practice, the vapor compression refrigeration cycle looks as this in the red color. So this system that is described over here and depicted on this TS diagram can be used as a refrigerator or a heat pump. When this system is used as a refrigerator, this temperature T2 at which evaporator removes heat from the cold space is lower than the temperature T4, that is the ambient temperature at which the condenser rejects heat to the ambient environment. Whereas when the system is used as a heat pump, its purpose is to heat the space to a temperature T4 that is higher than the ambient temperature T2. Therefore, a heat pump extracts heat from the ambient surroundings at temperature T2 and rejects heat to a high temperature heated space at temperature T4. The measure of performance of a refrigerator we've already seen is given in terms of the coefficient of performance, that is COP, and we've seen earlier that COP is defined as the heat that is absorbed by the refrigerator, that is in the evaporator section, divided by the work input to the compressor. So this is QL is the heat that is absorbed in the evaporator section, and QL is the rate at which heat is absorbed per unit mass flow rate of the working substance, and WC is the power input to the compressor over the mass flow rate of the working substance. Similarly, for a heat pump, the objective is to heat the space. Therefore, the coefficient of performance is defined as QH over WC. That is the heat that is rejected to the heated space divided by the compressor work. So besides this TS diagram to represent the vapor compression refrigeration cycle, often a pH diagram is also used. And this is because if we use a pH diagram, then we have two isobaric processes, that is the heat absorption and heat rejection processes, and one process, that is the throttling process, is isenthalpic. So that's why it is easier to depict the vapor compression refrigeration cycle on a pH diagram. On a pH diagram, the vapor compression refrigeration cycle looks like this. So this is our saturation dome. So state 1 is over here, and then in the evaporator heat is absorbed, and state 2, that is saturated vapor at lower pressure, is shown over here, and this process 2 to 3 is isentropic. And recall that the lines for constant entropy look like this, that is going from state 2 to state 3 on a pH diagram, and thereafter heat is rejected at constant pressure from state 3 to state 4, and only within this saturation dome the temperature is constant, that is from here to here, while pressure is constant because that is where condensation is taking place. Importantly, note that the process, that is the throttling process, is depicted by this vertical dashed line, and dashed line because this throttling process is an irreversible process, and we've already seen that in a throttling process, the enthalpy remains constant, and that's why this line is a vertical line, so that the enthalpy does not change as the substance goes from state 4 to state 1. So this is how the vapor compression refrigeration cycle can be alternatively depicted on a pH diagram. Finally, let us consider an example of a typical thermodynamic analysis of a vapor compression refrigeration cycle. So consider a vapor compression refrigeration cycle that uses R134A as the refrigerant, that is the working substance. Consider that the refrigerant enters the evaporator at a pressure of 140 kilopascals and enters the compressor at a pressure of 800 kilopascals. The mass flow rate of the refrigerant is 0.05 kilogram per second. So the question is to determine the heat removal rate from the refrigerated space and the COP, that is the coefficient of performance. The first step to do this analysis is to determine all these 4 equilibrium states, that is state 1, 2, 3 and 4. And once these states are determined, we can look at individual processes and find the heat that is removed, and we can find the work that is consumed by the compressor, and then we can calculate the coefficient of performance. So to do so, we look at the tables for R134A refrigerant. Now, to determine the various properties such as enthalpies at all these states, first we need to identify the equilibrium state, and to uniquely identify the equilibrium state, we need 2 intensive properties. So let's do that analysis. So let's begin by looking at state 2. So at state 2, we know that the pressure is 140 kilopascals, that is the pressure at which vaporization takes place in the evaporator, and we know that the quality of the vapor liquid mixture is 1, that is at state 2 we have a saturated vapor. So we know the pressure and quality, and we can look up at the tables, and from the tables we get the enthalpy at state 2 as 236.04 kilojoules per kg. So typically you'll have tables for the saturated states and for superheated and subcooled states, and this data you can get from the table for the saturation states. Next, at state 3 we already know the pressure. So pressure is 800 kilopascal at state 3, and to determine other properties we need to determine one more property, but we know that process 2 to 3 is isentropic, therefore S3 is equal to S2. So we can go back to the state 2 and we can find the entropy at state 2, and that is given by this. Now that we know pressure and specific entropy at state 3, so state 3 is now uniquely identified, and from the property tables we can get the enthalpy at state 3 as this. Next, we want to find state 4. So at state 4, we note that pressure is equal to that at state 3, that is 800 kilopascal, and another property we know is that at state 4 the substance is at a saturated liquid state, therefore the quality is 0. So using these two properties we can identify state 4 uniquely, and from the tables for saturated states we can get enthalpy at state 4 is equal to this. Finally, to find enthalpy at state 1 is straightforward because we know that process 4 to 1 is isenthalpic, it's a throttling process, so H1 is equal to H4, and that is 93.42 kilojoules per kg. Now that we have identified the enthalpies at every state, and every state is uniquely identified, we can calculate the various quantities of interest. So first we want to find is the heat that is removed from the refrigerated space. So the heat that is removed from refrigerated space is the heat that is absorbed by the evaporator, and that is equal to m dot times H2 minus H1. This is a straightforward application of the first law applied to a control volume, and in this case applied to the evaporator. So we'll get the mass flow rate is this, and the enthalpy change is H2 minus H1, and if we do that calculation we have 142.62, and therefore this is equal to 7.13 kilowatts. So the rate at which heat is being removed from the refrigerated space is 7.13 kilowatts for this case. Finally, let's look at the calculation for COP. So COP for a refrigerator is the heat that is removed from the refrigerated space, that is m dot H2 minus H1 over the power input to the compressor. So if you look at this compression step from state 2 to state 3, so this is an isentropic process. So the compressor is adiabatic and operates reversibly. So the rate of work input to the compressor from the first law is m dot H3 minus H2. Therefore, the COP is H2 minus H1 over H3 minus H2. So if you plug in these values, because we know all these enthalpies, you will get this to be 3.96. Finally, let's just compare this COP that we have obtained for the vapor compression refrigeration cycle with a Carnot cycle refrigerator that operates between the same low temperature and high temperature. The COP of a Carnot cycle, if these temperatures are TH and TL, recall that the COP is given by QL over the work input, that is QH minus QL, and for a Carnot cycle we have QH over TH is equal to QL over TL, that is the entropy that is gained during the process 1 to 2 is dumped during the heat rejection process for a Carnot cycle to go back to its original state. Therefore, this is the case, and then we have TL over TH minus TL. So if we determine these temperatures where vaporization and the condensation processes are taking place, we can determine the COP of the refrigerator working on a Carnot cycle in reverse. So we can go back to the property tables. So corresponding to this pressure, we can find the saturation temperature, and the saturation temperature for 140 kilopascals pressure is minus 18.8 degrees Celsius, whereas the saturation temperature corresponding to a saturation pressure of 800 kilopascals from the property tables, we can find that it is 31.33 degrees Celsius. Therefore, now we can compute the COP of this refrigerator operating on the Carnot cycle. So here the temperatures that we are interested in are the absolute temperatures. Therefore, we must convert into Kelvin scale. So we have 273.15 minus 18.8 divided by the difference in temperatures, that is 31.33, and minus of minus 18.8 is plus 18.8, and if you do the calculation you get 5.82. So as expected, the COP of the vapor compression refrigerator is less than the COP of a Carnot cycle refrigerator. Finally, note that the vapor compression refrigeration cycle that we have studied in this lecture is an idealization of what goes on in an actual refrigerator. And in a practical refrigerator, there would be irreversibilities, and such irreversibilities you can incorporate by incorporating efficiencies of the individual components.